Forget philosophy. What happens if a glass of water is truly, physically half empty? This thought experiment was inspired by Vittorio's question: what if, in an instant, a glass of water became literally half empty? It turns out the pessimist's view might be closer to the explosive reality than the optimist's. When we use the phrase glass half empty, we're picturing a container with equal volumes of water and air. The optimist, traditionally, calls it half full. The pessimist, half empty. Linguist Gretchen M.C. Kulik notes our choice of words often signals a process. Is the glass being filled or drained? Language is fascinating, but what if the void in the glass was an actual vacuum? That vacuum wouldn't exist for long. However, the precise outcome hinges on a critical detail most people overlook. Which half contains the nothingness? For this exploration, we'll set up three distinct scenarios. The standard air over water glass, a glass with a vacuum above the water, and one with a vacuum below it. Imagine these vacuums snap into existence at the exact same moment, time zero. For the initial few microseconds, almost nothing appears to happen. On this incredibly brief timescale, even air molecules are practically motionless. Most air particles vibrate and move at several hundred meters per second. Yet, at any given instant, a small fraction moves significantly faster than average. A few of these speedsters travel above 1,000 meters per second. These are the very first particles to leak into the vacuum space in our top vacuum glass. The bottom vacuum glass, however, is sealed by the water, preventing air from entering so easily. Water, as a liquid, doesn't expand to occupy the void like a gas. Instead, under vacuum conditions, it immediately begins to boil. The surface layer slowly transforms into water vapor, shedding molecules into the empty zone. The water in the top vacuum glass also starts boiling, but the deluge of incoming air will suppress this process before it can get very far. After a couple hundred microseconds, the situation escalates. Air flooding into the top vacuum glass completely fills the void and collides with the water's surface. This sends a powerful pressure pulse through the liquid. The glass walls flex outwards for a moment, but they are strong enough to contain the force and don't shatter. A shockwave bounces through the water and back into the turbulent air above. This pressure event takes roughly a millisecond to radiate outwards, causing the other two glasses to vibrate slightly as the wave passes through them. A few milliseconds later, this shockwave arrives at a person's ears as a sharp cracking sound. But are both vacuum glasses safe? Around this time, something dramatic starts happening to the bottom vacuum glass. It begins to visibly rise. The atmospheric pressure surrounding the container is trying to crush the glass and water together into the void. Think of it this way. At sea level, the air pushes down on every surface with significant force. For a typical drinking glass, the water's surface and the glass below it are being pressed down by nearly 45 kilograms of force. Usually, this is balanced by air pressure pushing up from underneath the glass. But in our bottom vacuum scenario, there is no counteracting force. Air pressure shoves the glass upward from below with immense power, while simultaneously pushing the water down from above. This is the mechanism we commonly call suction. The vacuum in the top half glass didn't survive long enough for this effect to lift the glass. But since the bottom vacuum is sealed, the glass and water accelerate toward each other. By now, the boiling has filled the void with a thin mist of water vapor. This doesn't matter. The glass and water are now moving far too quickly. Less than 10 milliseconds from our start time, they are flying toward one another at several meters per second. With no air cushion between them, just a scant trace of vapor, the water collides with the glass base with the unyielding force of solid steel. Water is almost incompressible, so the impact is not gradual. It's a single, violent shock. The momentary force exerted on the glass is astronomical, and it shatters. This phenomenon is known as a water hammer, the same effect causing the clanking you might hear in old pipes when a tap is shut off abruptly. It's also seen in cavitation, where collapsing vacuum bubbles erode ship propellers over time. In our case, the forces would be more than sufficient to obliterate even the thickest, most durable drinking glasses. A fun fact: Material scientists study fracture mechanics to understand exactly how materials like glass fail under such extreme, instantaneous stresses. Some reinforced glasses might resist, but standard ones stand no chance. So what do our observers see? The bottom of the glass is driven downward by the water, clattering onto the table. The water erupts outwards, flinging glass shards and droplets everywhere. A void isn't empty. It's a potential for violence. Meanwhile, the detached upper portion of the glass, now a projectile, continues its upward journey. After about half a second, the observers, having heard the initial pop, begin to react. Their eyes instinctively track the rising piece of glassware. The fragment has just enough velocity to strike the ceiling, breaking into more pieces, which then rain back down onto the table. If you've been enjoying these thought experiments, please give this video a like to support Winds of Thought. The lesson here is clear. An optimist sees opportunity. A pessimist sees a problem. A physicist sees a projectile.